So they want to make good parts, good quality parts. That means warpage free. And they also want to make them efficiently. They want to have lower cycle times. Okay, so both of those things relate back to the cooling. Part quality depends on the cooling quality, how uniformly the mold is cooled. And cycle time, of course, how efficiently you can cool the mold also relates back to the cooling design. So both of those things go into what would make a molder successful on molding parts. In many cases, you can't get straight drilled channels into areas like deep pockets where you have a couple of walls very close to each other. You just can't get cooling in there through conventional means, so you have to rely on a different technology. So that's where higher conductivity inserts come into play. So we get cooling into those inserts farther away from the part, but all the work is done by the insert itself. It's able to draw heat out at a faster rate, thereby cooling that difficult to cool area much more efficiently. Okay, so we take the mold maker's design, insert it into the cooling analysis, run an analysis, determine cycle time, a ballpark cycle time first. That determines what the surface temperatures are both on the core and on the cavity. So we're looking at the uniformity on both sides, and then we take the difference between the two, between the core and the cavity, to see if we've got a uniform differential between the two sides. If we find problems, that's where we start looking at either changing the cooling design to improve the cooling directly through conventional means, or looking at higher conductivity inserts. So oftentimes we get in situations where conventional cooling can't solve the problem, and we have to rely on higher conductivity inserts. So in order to do that, we need to be able to quantify how much of a problem we have. And until we can quantify it properly, we can't make that decision. So using the software with qualified engineers helps mold makers make that decision.